Hello everyone, my name is Ohana. I'm from QUT in Australia and SciTech in Germany. Today I'll be talking about closing functional coverage using deep reinforcement learning, and we'll be following through a specific example, a compression encoder. This is the agenda for today. So first of all, we'll talk about the challenges of closing functional coverage on complex designs. Then we'll have a quick introduction to reinforcement learning. What is reinforcement learning and how can it be integrated into RTL verification? We talk about our design, the LZW compression encoder, and why closing functional coverage on it is actually an issue. Then because the reinforcement learning agent and the RTL design come from very different worlds, we'll see how we can actually co-simulate both of them. And then I'll talk about the architecture of our DQN agent and how it tackles functional coverage. Then I'll show you some simulation results. There'll be some summary and conclusions, and if there are some questions at the end, I'll be happy to answer. As I assume we all know here, closing the last percentages of functional coverage on a complex design has always been a problem during the development of projects. So in this presentation, I would like to tap into some tools based on the reinforcement learning and some techniques that can assist us in our simulation to actually find the scenarios that could hopefully hit all the functional coverage bins. Specifically, we're going to use a deep Q-learning agent, and the technique is inspired by the work of DeepMind Technologies when they developed agents to play Atari games at a very, very high level. So yeah, that should be interesting. Here we can see a typical verification environment. We have the DUT right in the middle, and then the stimulus block generates transactions to be processed by the DUT. The DUT, on the other hand, drives the monitor with the output transactions. The input and output transactions are passed to the checker, which uses a golden model and does some scoreboarding between the golden model and the DUT output. And obviously during the simulation we execute functional coverage to see what's happening. Now if we move to the reinforcement learning world, we can say that the stimulus are actually actions executed on an environment, and in our case the environment would be mainly the DUT. So you can see the two red frames here, the agent and the environment. Once the DUT executes this action, the transaction, it responds by showing the state of the functional coverage and what we call a reward, which in our case would be positive if there has been a functional coverage hit, and null if nothing happened because of the action, which is here the transaction. Our design is an LZW compression encoder. This design receives input sequences of 4-bit symbols, compresses them, keeps sequences inside the design using car memory of 16 locations, and then outputs output sequences of 5-bit symbols each, which includes the 16 symbols from the input and the 16 addresses of our CAM. Now, if we define the functional coverage to be every possible write to this CAM, it turns out that we have 136 CAM write functional coverage bins, because on address 2 I can keep 2 symbols, and on address 15 I can keep 17 symbols. In order to hit all these functional coverage bins, I need to generate actually very specific sequences. If I use randomness in order to generate sequences, it is extremely unlikely to generate the sequences that I need in order to hit all my functional coverage bins. So that's why I would like to see if by using a DQN agent to generate these sequences, I can actually hit all my functional coverage bins, which are defined as all the possible cam rights for this design. Now my reinforcement learning agent is written actually in Python and PyTorch. And obviously my design is in System Verilog and is simulated also in a test bench written in System Verilog. So what I need to do is use a digital simulator in order to execute transactions on my RTL model and test bench. And I need to run a Python engine to calculate the next actions based on the DUT state and the functional coverage hits. Now they need to communicate between them. So for this purpose, I developed an interface based on a DPIC and embedded Python that talks to a communication socket also written in Python. And it's actually a client-server architecture where the RL agent is the server and our design is the client. So every time a state and the reward is ready, it communicates to the server and tells to the agent that it needs a new action. The agent receives the state and the reward, and using a neural network generates the next action, and so on with the target of maximizing the rewards, meaning maximizing the functional coverage hits, meaning hopefully generate transactions, which can hit every single cam right functional coverage bin. This is the architecture of our DQN agent. So the main element here is our neural network, which receives the DUT states represented as actually the functional coverage state, and based on it generates an action. This action is post-processed and generated as a transaction to the DUT. The DUT answers by telling us its new state and the reward. So the reward is actually equivalent to the functional coverage hit. So if there's been a functional coverage hit, there will be a positive reward. And if there hasn't been any functional coverage hit, there won't be any positive reward. So based on this reward, the DQN agent will update the weights, the parameters of our neural network, and hopefully can converge towards generating sequences that can hit all the functional coverage bins. What you can see in this slide is the simulation results for a standard randomized process of input symbols. So basically in this example, we are generating uniformly all the 16 symbols at the input of the DUT. And by doing that, we can see that in terms of cam overall occupancy, we can hit a maximum of around 44. But in terms of cam right functional coverage, we can hardly hit 29%. And this is by using a lot of transactions. So that means that the transactions generated form sequences which are not very interesting for the cam. And as a result, we have a lot of left out functional coverage bins. So now we're going to see how the DQN agent will run by looking at the functional coverage reward of the previous transactions and hopefully learn from them and generate sequences that can hit all the functional coverage bins. So this is the simulation of our DQN agent. So at the beginning, the transactions generated are also random, and based on the new state and the reward that the DUT provides to the DQN agent, the DQN agent learns what is good to drive in order to generate higher and higher rewards. Always in the future, the target of our DQN agent is to maximize the reward, meaning to maximize the hits on the functional coverage. And we can see that if we generate 2,500, 5,000, 7,500 symbols, we can see that slowly but surely and almost linearly, all the cam locations are actually occupied without any jumping in terms of cam locations, meaning that the sequences grow slowly but surely and occupy every single possible address of our cam. So by running here 500 episodes from cam empty to cam full, in this first simulation, I managed to hit 133 cam write bins out of 136, which represents 97.8% of the cam write functional coverage. So I have 3 left out functional coverage bins. So in order to hit them, all we need to do is actually run another set of 500 or maybe more, 750 episodes. And hopefully the functional coverage bins that have been left out can be hit this time, and we can merge both simulations to reach 100% functional coverage. So by running 2 sets of episodes, the first set of 500 episodes and the second one of 750 episodes, the DQN agent managed to understand the relationship between generating symbols and functional coverage hits. This understanding is actually modeled by the neural network, and because the target of our agent is to maximize the future rewards, the equivalent in our world would be to maximize the functional coverage hits. So it turns out that it managed to create the sequences necessary to hit every single functional coverage bins. This is what we were after. So here we can see that instead of trying to generate manually or trying to tweak the constraints of our randomization, the DQN agent does the work of actually generating the sequences which are necessary to hit all the functional coverage bins. So what did we see today? So first of all, we had the design an LZW compression encoder. We looked at the cam write functional coverage for this compression encoder, and we understood that we need to generate very specific sequences to hit all the 136 functional coverage bins of our cam. And for this purpose, we tried actually to use random generation, as would happen in a typical test bench, and we hit a very low percentage of functional coverage bins. So we used the DQN agent that managed to understand the relationship between generating an action and the functional coverage hit. This action has been modeled with a function embedded in a neural network, and because the target of our agent is to maximize future rewards, meaning to maximize functional coverage hits, we managed to generate all the sequences necessary in order to hit all our functional coverage bins. Now, if there are any questions, I will be happy to take them. Also, there's an additional slide at the end of the presentation that highlights the main formulas of our DQN agent if anyone is interested. The DQN agent in equations. A deep Q network, DQN agent, basically uses a neural network in order to model an action value function. An action value function is a relationship between an action and the value that I will get from the environment out of this action. Our action value function is called QPy SA, where S is the state and A is the action. What it actually does is just to process the environment state called S and issues an output vector value where every element of this vector represents the expected future reward called R for every single action. It is the expectancy of the reward based on the action and the state with a policy pi. In our case, the policy is just a way of selecting the next action to drive out of all this vector. Now, if we move to the verification realm, what I said just means that given the functional coverage state, every input symbol that we can choose for the next transaction has a particular impact on the CAM-right functional coverage overall score. So what I want to do here is maximize the reward, meaning maximize the functional coverage, meaning that I will choose a symbol that will hopefully generate a new hit or a bigger hit in the functional coverage. And this way, from my point of view, will cover the missing functional coverage pins. As I said, pi is also called a policy and is just a way of selecting the next transaction from the output vector, expectancy of R based on the action, the states, and the policy pi.